Let's work some examples with probability of independent and dependent events. First, we want to look at a few definitions. Two events are independent means that the first outcome, well, if they're independent, they don't depend on one another. So that means that the first outcome does not affect the second. When two events are dependent, it means that the first outcome does affect the second. So as we're looking through some examples here, we're going to start by identifying which of these are independent events and which are dependent events. So first we want to look at tossing two coins. So if I toss two coins, the two coins have nothing to do with one another. We're going to assume that they don't hit each other up in the air or anything. Whatever happens to the first coin has nothing to do with what happens to the second coin. So that tells us that we're going to treat those as independent events. Okay, next. The gender of the next two births at a hospital. Well, the gender of one child doesn't have anything to do with the gender of the next mother's child. So these again are independent events. Number three. So number three, now we're drawing two cards without, and that language is really important, without replacing the first. So that means that we're taking, so maybe it's the Ace of Hearts. We're taking that Ace of Hearts out of our deck, and we've actually shrunk the deck by one. So the next card that I pick has changed in probability because there's one fewer card in the deck. These are dependent events. For number four, we're going to draw that first card, but then we're going to put it back into the deck. Since we are replacing that first card, we have the same number when we draw from the first and when we draw for the second card. So now this becomes two independent events. And then finally, flipping one coin and rolling two dice. Well, whatever happens to the coin has nothing to do with what happens with those two dice. So there are three events here, and all three of them, are independent. I almost circled the wrong one. So all three of these are independent. Okay, let's go ahead and take a look at some probabilities. So we're going to draw two cards from a deck. This time it's going to be without replacing the first card. So that means that when I draw a card, it's gone. It's no longer in that deck of 52 cards. So a couple things to remember about a deck. So I've got 52 cards. There are 4 suits, and I'm going to show you the deck here in just a second. 13 in each suit. There are red cards and black cards, so half the deck, so 26 of the cards are red. Half the deck, 26 are black. Okay, and that's a 3. So 13 cards in each. I do have a deck of cards right here, which is there. So you can see what that deck of cards looks like. I'm actually going to grab this and let's bring it up so it's closer to this first example as I work it. I also have let me grab it here. So I've got a tool that will allow me to grab a deck out of a card. Grab a card out of a deck. So I'm going to go ahead and grab this first card and then we'll build a probability based on that. So the first card is a jack. So let's go ahead and make this probability, the probability of choosing 2 jacks. We can make this smaller so that we can see both. Okay, so we want to know the probability of getting 2 jacks. I have right now drawn the jack of hearts, so I can cross that jack out. So when I drew that first jack, so this is a probability of a jack and a jack. When I drew that first jack, there were 4 of them in my deck of 52 cards. This word "and" is going to be translated as a multiplication. So it's a lot like when we're choosing things for an outcome. So if we want a pair of pants and a shirt and shoes, we multiply all those choices together. So we're going to do the same thing here. So we're going to multiply it by that second draw. When I go to draw another jack, I notice that there are only 1, 2, 3 jacks remaining. So the probability of getting a second jack is 3. And I've taken 1 card out of the deck. So there are 51 cards remaining. And you can see that over here in my Shuffled Deck app. It says that I've drawn 1 out of the 52 cards. When you're doing these probabilities, you assume that the first draw is what you're looking for. That's the only way that you can come up with the correct theoretical probability. Well, let's see if we're right, and then we'll do the calculation. So I'm going to go ahead and draw a second card, and I wasn't right. Not a really big probability here. I'm going to go ahead and multiply this together, and I'm going to do that in my calculator. So let me grab my calculator, which is right here. So for my calculator, apply the numerator first. 4 times 3 is 12. So as a fraction, we're going to get 12 over. My denominator is 52 times 51. So my denominator is 2,652. If I write that as a decimal, so I can get a percentage as well, I would do 12 divided by 2652. And I end up with a really, really small probability of choosing 2 jacks. So I've got my decimal there. If I move 2 decimal places, I get 0.45%, less than half a percent of choosing 2 jacks. So let's go back and do another one of these. I'm going to erase what I've done here so we can do this again. And let's move on to part B. So for part B, I'm again going to do another example here, and I'm going to choose my first one. So I'm going to grab my shuffled deck. I've got 52 cards now, so I've essentially reshuffled the deck. I'm going to draw a card. This time I got a 6 of spades. So for this one, I'm going to say that I want to choose 2 black cards. So what's the probability of getting 2 black cards? Remember, there are 26 of these in the deck. Right now I've chosen 1 of them. So I've chosen the 6 of spades, which is this one. So I've crossed that one out. When I put my probability together, this is going to be the probability of getting a black card and a black card. I put that together as the first probability times the second probability. The first probability, there were 26 to begin with, over my 52. You could also write that as 1/2. Now I've taken the 6 of spades out, which means that I have 1 less black card. So that's going to be 25. I've also taken one of the cards out, so that's going to be over 51. So let's see if I get another black card, and I don't. So I'm not really lucky today, am I? Let's go ahead and grab the calculator. There it is. So we'll go ahead and do our calculation here. I want to do 26 times 25 for that numerator, and I get 650. And I have the same denominator, that 52 times 51, 2652. So I'll go ahead and do 650 divided by 2652. And this time I end up with a pretty decent probability, so about 25%. So here we get 24.5%. Okay, I think I've got one more of these. So again, let me go ahead and erase what we've done. And let's go down to the next one. Okay, so one last probability with the drawing 2 cards without replacement. I'm going to go back to my deck. I'm going to reshuffle that deck, and then we'll go ahead and draw one. So go back to my shuffled deck. I'm going to go ahead and draw one. This time it's a 6 of diamonds. So I want to know what's the probability of getting 2 diamonds. So I'm going to do 2 diamonds this time. So I know that that becomes the probability of getting a diamond and a diamond. There are 13 of each suit. So all of these right here are my diamonds. So when I start out trying to get that first diamond, so the first diamond times the second diamond, there are all 13 of them. So I have 13 divided by 52. I drew the 6 of diamonds, so I can go ahead and cross the 6 of diamonds out. When I go to draw the second diamond, there's only 12 left. I've also taken that card out, so I end up with 51 cards in total. As I calculate this one, I get the same denominator again, but my numerator changes. So for the numerator, we're going to do 13 times 12, divided by 52 times 51, which is 2652. And we end up with a pretty small probability, so about 5.9% this time. So about 5.9%. Let's see if I get a second diamond. Chances are not good, and I don't get a second diamond. Okay, so you'll notice a couple things though. As I'm looking, and I'm just going to use this last example. So as I'm looking at this last example, you'll notice what happens when we go from the first, when we go from the first numerator, grab that. So when I go from the first numerator to the second numerator, I'm counting down. I do the very same thing when I go from the first denominator. I had all 52 cards to begin with, and then I count down to get to the second denominator because one of them has now been drawn. When I look back at all of these examples, you'll see the same pattern. I start with 4. These were our, what were those? The jacks. I start with 4 jacks. I go down to 3. I started with 52 cards. I go down to 51. For the black cards, I start with 26. I go down to 25 because I assume I chose a black card to begin with. I start with 52 and I go down to 51. So once you start seeing these patterns, it's really nice and fairly intuitive to put these guys together. Let's go ahead and look at the next set of questions. In the next set of questions, I'm actually going to get rid of this. So in the next set of questions, we're actually looking at the same setup with one tweak. So now we're going to be drawing 2 cards, but we're going to replace that first card. So we have changed what was a dependent set of events into independent. These 2 draws no longer depend on each other. So I can just go ahead and use this guy. Come on. So if I just go ahead and grab that, I can go ahead and just draw it down so we can see it. I draw my blue pen as well. Okay, so I've got my independent events. The probability that I draw 2 cards now. So for this one, let's do 2 queens to start. I'm going to erase what I've got here. We want to draw 2 queens, so I start with all 4 queens in my deck. I assume that I draw one, so there's a 4 out of 52 card chance. There are all 4 of my queens, but I don't cross anything off. I don't take it out of my deck. Instead, I put it back into the deck. So if I drew this queen, I put her back into the deck. There are still 4 out of the 52. So I end up with 4 times 4 in the numerator, which is 16. I need to compute that denominator, 52 times 52. 52 times 52, and we end up with 2,704 for that denominator. To get to that probability, let's just do that division. 16 divided by 2,704. And I end up with a really small probability, about 0.6, so about 0.6%. So just a little more than half. For the second one, let's do the probability of getting 2, let's do two aces this time. So if I look back up at my aces, there are 4 of them. I'm going to assume I draw this one. It doesn't matter which one we draw, but I do assume that the first one is a draw. So this is the probability of an ace and an ace. So ace times ace, there are 4 to start with, 52 in the deck. I draw that card, but then I replace it, so I put it back in the deck. I don't cross it off this time. So when I go back to draw a second card, there are still 4 aces out of the 52. I know my numerator is going to be that same 2704, same numerator, sorry, and denominator. So we again end up with 0.6%. So that's for both A and for B. For part C, let's do the probability of drawing 2 face cards. So this is going to be the probability of a face card and a face card. Let's go up to our deck of cards diagram. In our diagram, our face cards are over here. So for the face cards, we have 3 per suit. So there's 3, 3, 3, and 3. So that's going to be 12 face cards all together. When I draw any of these face cards out, there are 12. So I have a 12 out of 52. So this is face card and face card. So 12 out of 52. I put whatever face card I drew, put it right back into the deck, and again do another draw. All 12 face cards are there. All 52 cards are there. I have the same numerator, or sorry, the same denominator, but this time I've got 144 for my numerator and that 2704 for the denominator. So as I do that math, so 144 divided by 2704, we end up with about a 5.3% chance. So this one, I'm going to write it right here, is about 5.3%. So when we're doing these with replacement, you'll notice that the numerators and denominators stay the same. 4 goes right back to 4, 52 goes right back to 52 because I'm putting that card back in the deck. Let's take a look at question number 3. In question number 3, we buy 3 lottery tickets. Each of them has a 1/5 chance of being a winner. What's the probability that all 3 are winners? So we're looking for the probability of winner and winner and winner. That and tells me that I want to use the multiplication rule. So the probability that the first one wins times the probability of the second times the probability of the third. Each of them has a 1/8 chance of being a winner. So just because you end up with one winner to begin with, it has no effect on whether or not the second one is a winner. These are independent events. So that means if they're independent, I can go ahead and put the same 1/5 probability for each of those. 1/5. So 1/5, 1/5, and 1/5. 5 times 5 times 5 is 125. So I can go ahead and just do that math quickly to get a percentage. So 1 divided by 125, we get 0.008, really small percentage here, or 0.8%. So really small, 0.8%. So independent versus dependent events. Here's an example. We're using data or results. So we are looking at empirical probability, which we also call the relative frequency probability. We're going to use the chart to answer these probability questions. So if we choose one person at random, what's the probability that that person is type O? Well, based on our chart, the probability that a person in the US is type O is 45%. So I can just write 45%. What's the probability that they're a type A or a type O? Now I want to take both of these together. So this OR is telling me to add those probabilities together. So that's going to be 45 plus 40%. So we end up with an 85% chance. And then finally, what's the probability that they're not type O? Let me erase my things I've circled here. If they're not O, that means that they're one of these other types. So not O would be a type A, which would be 40%, type B, which would be 11%, type AB, which would be 4%. So that's what, 40 plus 15? 40 plus 15 would be 55%. For number 2, still using this chart, I'm going to choose 3 people at random. What's the probability that all 3 are type O? I reread this one as the probability of the first one being O and the second one and the third one. There's that multiplication principle. So the probability that the first person is type O, second person is type O, and third person is type O. For this one, these are independent events. One person being type O does not affect the other. So each of them are going to have the same probability of 45%. So I'm going to do 0.45, 0.45, 0.45. So on my calculator, I'm just going to take 0.45 times 0.45 times 0.45. Okay, and we end up with 0.0911, so about 9.1%. Part B also has multiple events, so we've got all three, but this time we want all three not O. So this would be the probability not O, and not O, and not O. So putting this together, again, I want the multiplication principle. So that's going to be the first one's not O, the second one's not O, and the third one is not O. To not be an O, that means they're one of the other three types. We've already done the probability that one person isn't type O, and that's 55%. So each of the people has a 0.55 chance of being a type other than type O. So to come up with my answer here, I want to type in 0.55 times 0.55 times 0.55. And we end up with 16.6%. So I get a 16.6% chance. So for number 2, we have multiple events. 3 people. In part 1, we have a single event because we're looking at the probability of a single person being one of those blood types. Now for part E. A widespread virus is said to hit the U.S. about every 4 years. So again, we're using empirical or a relative frequency probability based on data, based on past events. What is the probability that another virus will hit in 2024? So one about every 4 years. So this would be favorable would be 1 out of total would be 4. So I can use that same theoretical probability idea, favorable out of total, or 0.25. So that's the same process that we use even for empirical or relative frequency probabilities. What's the probability that a virus will hit in 2 consecutive years? So these are 2 events, right? 2 consecutive years. So this would be the probability of getting a virus and the next year getting a virus. So I want the probability of getting a virus for each of those years. That's going to be 1/4 times 1/4, or 0.25 times 0.25, same thing. I'm going to end up with 1/16. You could also multiply the 0.25s together. I'm going to do 1 divided by 16 though, and we end up with 0.0625, so 6.25%. 6.25%. Okay, part 3. What's the probability of no such virus happening in the next 5 years? So as I'm doing this one, it's going to be no virus. I'm going to write NV, and no virus, and no virus, and no virus. 1, 2, 3, 4, one more, and no virus. So I want to put this together as first year without one, second one without one, third year without, fourth year without, fifth year without. If there's a 25% chance that there is a virus, we can do 1 minus 0.25, and that gives me a 0.75 chance of no virus. Using that opposite idea. So I can put this together by doing 0.75 times 0.75 times 0.75, right, 5 times. don't think my calculator has a fifth power on it. If it did, I would definitely use that. But instead, I'm just going to go ahead and multiply this. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 looks great. So I've got about a 23.7% chance of no virus. So 23.7%. Finally, number 4. What's the probability that the U.S. will be hit by at least one virus in the next 5 years? So at least one virus could mean one virus, or 2, or 3, or 4, or a virus all 5 years. The only thing it doesn't mean, but not 0 viruses. We've already done the probability for 0 viruses. So the case that I'm looking for this at least includes all of those cases. So instead I'm going to use this opposite idea, and I'm going to take 1 or 100%. I'll do 100%. And I'm going to subtract the only case that I don't want. I do want to include the case for 1, for 2, for 3 years, for 4 years, or for 5 years. But I want to take out the case for no viruses. So the probability that no viruses in 5 years. So I take out the case that I don't want. So 100% minus 23.7%. And I'll do that over here in my calculator. So 100 minus 23.7. And we end up with that probability of 76.3%. So when you get to one that says at least, you're going to take 100% and subtract the probability that you don't want. And in this case, it was the probability that we had no viruses during those 5 years.